Hi everyone, this week we're going to learn about approximate integrals, or rather approximating integrals, I think would be more accurate. Um, well, you've already seen that finding derivatives is rather easy and finding antiderivative is not. Because you can basically find the derivative of any function, but finding the antiderivative is not always possible. For example, e to the x squared. We used a method to approximate that within certain bounds, but to find the exact algebraic expression is not possible. Similarly, for square root of 1 plus x cubed. Notice this is x cubed, not x squared or x to the 4, which we know we can use some sort of trigonometric substitution to make that work. On second page, you should be able to see it now. Okay, there we are. So yeah, we saw the approximation for the first integral in the previous homework. Now we're going to learn a few methods which are classified as numerical methods of approximating different integrals. In order to learn these methods, we need to recall something from Calc 1 called Riemann Sums. Yeah. So the basic idea was that you can find the area under a graph by breaking things into rectangles. Now we say that this integral is approximately equal to the summation, where the summation is the function, that's f of xi star, which is the height, and delta x, which is the width. So you're finding the area of each of these rectangles, and you're saying, well, it's approximately equal to the area under the curve. When finding Riemann sum, we say that this xi is between x0, x1, x1. So we take any sample point we want as the height, right? That's what we say. And then the delta x is b minus a over n, where b minus a is your total length, and n is the number of rectangles used for, approximation. Now here we can make some arbitrary choices. We can say that instead of taking any sample point, let's take the left point, which is what I've done here, and that's called the left approximation. Similarly, if I take the right point, we get the right approximation. So left approximation would give you something like that, whereas right approximation would give you, so here, the right point is giving you the height for each of the rectangle, and that's why it's a right approximation. Here, the leftmost point in each interval is giving you the height of the rectangle, so it's a left approximation. So that's the basic idea, meaning we are approximating them using rectangles. So that's how we're going to be using, or we'll see the methods. The first method is called the midpoint rule. It's pretty clear by the rule, name of the rule, that you average out the left and the right endpoints by setting xi star is xi minus 1 plus xi over 2. So you're basically taking, remember, if you take xi minus 1, then that's your left approx. If you take xi, it's your right approx. So you're taking the midpoint of them. This is what the figure would look like. If you have 4 rectangles, then you take the midpoint, and that midpoint, the function value corresponding to the midpoint, would become the height of the rectangle. So it's it's kind of like, well, it is a midpoint of both. Explicitly, that would be delta x, which still is the same, which is b minus a over n, f of x1 bar, x2 bar, xn bar, depending on how many rectangles or the value of n, where the bar value is just the average. Xi bar is average. Let's look at an example. Let's approximate 1 over x, integration 1 to 2 with n equals 5. Now first we find delta x, that's b minus a over n, 2 minus 1 over 5, which is 0.5. Starting at 1, that would put me at 1, 1.2, 1.4, 1.6, 1.8, and 2. Now the midpoint for the first one is 1.1, and then I can just add 0.2, which is delta x plus delta x, to get the subsequent points, which are going to be 1.1, 1.3, 5, 7, and 9. So this integral is just going to equal delta x, which is 0.2, over f of 1.1, which is, remember here, f of x is 1 over x. That's what we are integrating. So 1 over 1.1 plus 1 over 1.3, so on, gives me this. You can verify, you actually can find this integral explicitly. It's log of x, which gives me log of 2, which is 0.693147. So it's close enough. The second method of approximation is called trapezoidal rule. Now, instead of averaging the endpoints we did with the midpoint, we average the actual right and left, they should say, approximations. So I add the left approx to the right approx and I divide by 2. Now if I expand these out, this is going to be delta x over 2, sum of f of xi minus 1 plus f of xi. Further, I expand this, that's f of x naught plus f of x1 when I is 1. This is when I is 1. And this is when I is 2. This is when I is n. So what you'll notice here is that f of x1 appears twice, f of x2 appears twice. Everything appears twice except the first one, which is f of x naught, and the last one, which is f of xn. So this is the trapezoidal rule. It's delta x over 2 f of x naught plus 2 f of x1 till f of xn minus 1, and then f of xn. Where delta x, the definition remains the same, b minus a over n. Xi is a plus I delta x. Okay, let's do the same problem with trapezoidal rule. Okay. Now here we are not using any midpoint, so we're going to stick with 1, 1.2, 1.4, 6, 8, and 2. But we have f of 1, and then we have 2 times of all the other function values, and 1 f of 2. This gives me 0.695635. Now the next goal, which we'll learn in the next video, is to understand how good each of these approximations are.